Position vectors. Consider the point A, which has coordinates 8, 4, and the point B, which has coordinates 4 along, 9 up. Now, what I want to do is to work out the components of the vector AB. How do I get from A to B? Well, what we could do is just, we could count the boxes. So AB, how do we get from A to B? I hope you can see that we move, that's 1, 2, 3, 4 backwards. So that's going to be, we have an x component of -4, and then 1, 2, 3, 4, 5 in the positive y direction. So -4, 5. Now, it's not always convenient to draw a diagram and to proceed in that fashion. So what I want to do now is to consider another way of working out the components of the vector AB. So what I'm going to do is, I'm going to mark the origin O, and I'm going to draw a dotted line from the origin to the point A. I'm going to call that the vector small a. Here is the origin here. And the components of the vector small a, well, so small a underline, we could also call that vector large OA, arrow above. So how do we get from the origin to the point A? Well, it's 8 in the positive x direction and 4 in the positive y direction, so its components are 8, 4. I'm going to do something similar with the point B. So here is a vector which I'm going to call small b underline, and if we work out the components of the vector small b underline, which we can also call OB, arrow pointing from O to B, then it has components. So starting with O, it has components 4 in the positive x and 9 in the positive y. Now let's go to our diagram. So we're going to start at the point A and we want to finish at the point B. How do I get from A to B? Well, the direct route is fine, but there's an alternative route, which I hope you can see. That's when we go from A to O, and then from O to B. So we go in this direction here, we go from A to O, and then from O to B. A to O, and then from O to B. Now, A to O is a bit of a problem. We know what OA is, but how do we deal with AO? Well, that is negative. Now we know that OA can be written as small a underline, and we know that OB can be written as small b underline. And rather than have it in that form, what we can do is we can write it as b minus a. So B has components, small b underline has components 4, 9, and then minus 8, 4, and 4 take away 8 is minus 4, and 9 take away 4 is 5. And lo and behold, we have exactly the same answer as we got up here. What we can say in general, this line is very important here. What we can say in general is that AB can be found by subtracting A from B. And these are the position vectors here. That's the position vector of the point B, and that's the position vector of the point A. So if I have coordinates, the coordinates of the point A are 8 along, 4 up. I can then go to the position vector of the point A and write the coordinates as a column vector. Similarly for B, B has coordinates 4, 9, so the position vector of the point B has components 4, 9, written as a column vector. Example 1. What we don't need to do is have a diagram, we need some points though. Let's take the point P, which has coordinates -3, 5, and the point Q, which has coordinates 4 along, 2 up. Now what I can do immediately is go from the coordinates of the point P to the components of the position vector of P. So I'll write that as -3, 5 as a column vector, and Q underline is 4, 2. So if I want to work out the components of the vector PQ, PQ is small q minus small p, 4, 2 minus -3, 5, 4 minus -3 is 7, 2 minus 5 is -3. Now if we were to sketch this information on a diagram, we would find that it was correct. And this will allow you to do page 110, exercise 13.3 of the vectors booklet. Calculating the magnitude of a vector. Example 1. We have a vector A, which has components 5, 4. Work out its magnitude. Now what we could do is, we could just pick a starting point here, and we'll draw the vector. So it's 5 on the positive x, and then 4 on the positive y. So starting point to finishing point, arrow pointing from start to finish, and A underline. What we want to do is to work out the length of that line, but not by measuring, by calculation. Now, I'm going to put in a dotted line indicating the x component and the y component. What we've just done there is created a right angle triangle. This side is 5, which corresponds to the x component, and this side is 4, which corresponds to the y component. What we're going to do then is apply Pythagoras. So now there's some notation that we use here. Remember, Pythagoras tells us that a squared equals b squared plus c squared, where a is the hypotenuse. For a vector, it looks like this, and these are called magnitude bars. And these will often, if not always, appear in a vector calculation involving magnitude. So what we're going to do, we're going to square the x component, we're going to square the y component, we're going to add them together and take the square root of the total. Taking the square root was the last thing we did in a Pythagoras calculation. So that's 25 plus 16 rooted gives us the root of 41, and we can leave it like that. There's no need to reach for a calculator and change that into a decimal. Example 2, we've got coordinates of r, 3 minus 1, and the coordinates of s, 6, 4. What we want to do is to work out the magnitude of the vector rs. So these are the magnitude bars that I was speaking about. That means that we want to work out the length of the line joining the points r and s. Now we don't need to use a diagram. We know that we can go from the coordinates of a point to the components of a position vector. So the point r, 3 minus 1, has a position vector, small r, 3 minus 1. The point s, 6, 4, has a corresponding position vector, s, with components 6, 4. rs, the vector rs, is found by subtracting r from s. So it's 6, 4 minus 3 minus 1, and that gives us 6 take away 3 is 3, and 4 minus minus 1 is 5. Now the last thing that we want to do is to work out the magnitude of the vector rs. So include the magnitude bars. We square the x component, square the 3, square the y component. So we'll square the 5, add them together, take the square root of the total. That gives us root 34. So you can now do page 111, exercise 13.4 of the vectors booklet. Alternative vector journeys. Write each vector in terms of A and or B. Now these really should be A underline or B underline. We'll not worry too much about that. So the first thing then is the vector BA. Now we've got a slight problem because we look at the diagram. We know that the vector AB, arrow pointing from A to B, you can see that in the diagram, the arrow points from A to B. So when we write down the vector AB, the arrow points from A to B. AB can be written as small a, and while we're at it, BC can be written as small b underline. So how do we get from AB to BA? Well, we reverse direction. So BA is negative AB, and that is negative A. AC, let's see, if we look at the diagram, how do we get from A to C? We start at A, we go to B, and then we go to C. So A to B, and then we add on B to C. Now we know that AB is A and BC is B, so AC can be written as A plus B. DB, let's look at our diagram, so D to B. Now we can go from D to A and then A to B. The only problem is we know nothing about the vector DA. So there is another way of getting from D to B. We can go from D to C, because we know that that's 2A, and then we can go from C to B. So that's DC plus CB. DC is fine, but look, C to B, we're going against the arrow. So CB can in fact be written as minus BC. DC is 2A, and minus B. The last thing we'll do is part D. So AD equals A to D. Well, again, we don't have any information about this line here, but we do know that we can go from A to B, B to C, and C to D. So there are three stages: A to B plus BC plus CD. So AB is fine, that's A, small a underline. BC is fine, that's small b underline. I hope you can see that CD is going to be minus 2A because we're going against the arrow. So if we simplify, A take away 2 is minus A, so it's B minus A. Second example on alternative vector pathways. Now we want to work out AB. Well, what we can do is, so here is AB here. We don't know anything about that line. We do know, however, that we can go from A to F and F to B. A to F is going to be negative A because we're travelling against the direction of the arrowhead. So that's minus A plus B. And we would normally write that as B minus A. FO. F to O, well, this is interesting. F to O is exactly the same as A to B. So this is a regular hexagon. These sides are parallel, or these lines are parallel, and exactly the same length. So FO equals B minus A as well. And there are a number of other lines which are exactly the same. For instance, O to C and E to D. Part C, AO. Now A to O, here's AO here. So A to O is A to F plus F to O. A to F now A to F is minus A, and F to O, oh here it is here, it's B minus A, so plus B minus A, and we'll write that as B minus 2A. And the last thing is FD. F to D. Now, F to D. Well, we know that this line here is the same as this line, and the same as this line. What about this line here? Well, F to E is the same as A to O, and I've just found out that A to O is B minus 2A. So let's see. F to D is FE plus ED. F to E is the same as AO. So this line here going from F to E is exactly the same as going from A to O. And E to D is exactly the same as A to B. So that's B minus 2A and AB is B minus A. So that gives us 2B minus 3A. So you can now do page 113, exercise 13.6 of the vectors booklet. Three-dimensional vectors means that we have three components. So for instance, we could have the vector A with components 3, 4 and 5. This is the x component, the y component and the z component. Now what we have here is a 3D coordinate grid. This is the x-axis, this is the y-axis, and this is the z-axis. To get some idea of how this operates, try to imagine sitting at your desk in the classroom, and here's your desk here. And this would be the origin of the coordinate system. Now the x-axis is you moving along the front edge of your desk. That's the edge closest to where you're sitting. The y-axis would be along into the surface of the desk, and the z-axis would be coming out of the desk. So x and y and z. It can be difficult to draw that, so if we wanted to plot the point, or to draw the vector A with components 3, 4, 5, so we could maybe start here. We'd go 3 on the positive x, 4 on the positive y, and then 5 up out of the page like so. And so if we were joining start to finish, this would then be our vector A. What else can we do? Well, we can work out the magnitude of the vector A. So we square the x, square the y, and square the z components, add them all together and take the square root of the total. 9 plus 16 plus 25. And that's root 50. If we have a second vector, vector B, which has components minus 4, 6, 2, well, we can add these two together, just as we do vectors in 2 dimensions. So 3, 4, 5 plus minus 4, 6, 2, and that gives us 3 plus minus 4 is minus 1, 4 and 6 is 10, and 5 and 2 is 7. What about the vector 2a? Well, it's simple. We multiply the components of a by 2. 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, and so on and so forth. One last thing we might want to do is, if we had the point P with coordinates 5, 0, 7, and the point Q with coordinates minus 3, 3, 4, can we work out the components of the vector PQ? Well, the position vector of P would be 5, 0, 7 as a column vector, and the position vector of Q would be minus 3, 3, 4. So if we want to work out PQ, it'll be Q minus P, so it's minus 3, 3, 4, minus 5, 0, 7, and that gives us minus 3 minus 5 is minus 8, 3 take away 0 is 3, and 4 take away 7 is minus 3. You can now do page 114, exercise 13.7.